to 25. The 2022, this is multiple choice from 14 to 25. The addition reaction of propene and hydrogen bromide is a two-step process. Which of the following shows the first step in this mechanism? Okay, so first of all, you need to know that this is a hydrogen halide, so I'm looking for a carbocation intermediate. Okay, that helps you a lot because it basically gets rid of these two. Okay, I can get rid of C and D because we don't have a carbocation intermediate here. We have a cyclic ion intermediate. Okay, so in this case, what you'd be looking at here would be the addition of a full halide, so it would just, or halogen rather. So like if it was BR, not HBr. Okay, so now we just got to work out, since everything else is the same here, we don't have anything fancy going on with different carbocations because it's propene and therefore symmetrical in this. So what we're looking for is just the right attacks of the curly arrows. Okay, so what we need to do here is to basically use the electrons from the double bond to attach on the hydrogen, which will then bounce out the electrons that are in this bond so that the bromide ends up as a negative. Okay, now you've got the bromide getting both times, you're getting the bromide to a negative, that's fine, but on B we've got an attack when we need to actually have the electrons being shown moving to the hydrogen, which is why it's A. Okay, synthesis questions, never the loveliest. Question 15, and this is just a reasonably straightforward one. Which of the following contains a phenyl group? So phenyl is where you have normal, oh that's a terrible version of benzene, give me a sec. Okay, where you have benzene, okay, which is either shown like this or occasionally shown with the double single, okay, where you have taken one of the hydrogens, because remember every single one here has a hydrogen attached. You've taken one of the hydrogens and you now have a different substituent group. So we normally draw it, if we were looking for a kind of clean, easy version, like that. Okay, unfortunately they've not given you that. So let's just deal with what it isn't. It's not A because there's a nitrogen in the middle of the ring, and that's not benzene. It's not B because there are no double bonds in here, that is just a cyclohexane that you've got there. Well, cyclohexanol because you've got an OH at the side. We look at C and it's looking better. We do have a double single going on over here with this ring on the right, but we're connecting into two carbons in the middle of that to make a double ring. So no, not C. D, however, I've got this one, that's a phenyl. Okay. Question 16. Considering the following reaction sequence, 2-chlorobutane, we've got a cyano group going to X, and then we've got hydrogen ions and water going to Y. Okay, so you need to recognize what's going on here. What we're doing here is we are substituting in a nitrile group, so we're basically putting this in place of the chloro. Basically we're getting rid of the chloro, so that's your substitution has happened here. And then we are doing basically a hydrolysis on this one, so we are changing this one now into a carboxylic acid. Now what they do always is, you can see, add a carbon in. Okay, so we're expecting that our 2-chlorobutane, we would end up with the nitrile group of number 2, and then we're going to end up with our butane has been increased in terms of size of numbers. So if I take my 2-chlorobutane to start with, and this is what I would have been doing in the exam, I would have been doodling them out, okay, and then I'm going to change it by substituting in my nitrile. Okay, and then I'm going to change it again and make that into the carboxylic acid. Okay, give myself a little bit more space. So there's my C, double bond O, bond OH, and then it's just normal Neyman rules. So here's my longest chain. Okay, so that's methylpropute. So I'm making butanoic acid. Okay, and I've got a methyl group of number 2. So 2-methyl butanoic acid. And that's it. Okay. Question 17. What is the systematic name of the molecule shown below? So this molecule has been given in skeletal formula form. Just to check if you can do it. That's obviously why they've got that there. So let's draw it out in full, if that helps. Okay, so we've got a CH3 at the end, and then we've got a CH2. We've then got an O in the middle here, a CH2, CH2, a CH, a CH3, and a CH3 coming down here. Okay, so this is what makes it an ether. Okay, so we've got an oxy. Okay, and they've been reasonably nice. They've told you it's ethoxy, and you're like, well, it must be because this is your kind of side chain, which means this is your main chain. Okay, so our main chain is methethprobute. Okay, and that gets you there actually. Oh no, it doesn't quite. Sorry. This is your, so you've got bute. And then you just need to number things properly. Okay, so we want this to, our main chain, the eth is the bit that wins. So we've got 1, 2, 3, 4 on this one. Okay, so we've got one ethoxy, and we've got a methyl group of number 3. So 1 ethoxy, 3 methyl butane. Okay, question 18. When propanone dissolves in water, the following equilibrium is established. We've got a ketone going to an enol. You don't know anything about these really, this is just telling you something. Okay, so the ketone and the enol are isomers and are called tautomers. Which of the following ketones does not have an enol tautomer? Okay, so you can do this several ways, but what you should be recognizing in here is that we have a kind of thing down here which is going to cause problems. In fact, this is what gives you the right answer. This is a tertiary in terms of where the carbons are on either side. Okay, so what we've got on either end of this, you've got a C double bond O, and then you've got a C with a C, a C, and a C, and then you've got a C with a C, a C, and a C. So basically, these carbons are going to make it impossible for you to basically lop one off and move it around and get an OH basically in here. Okay, so if it can't go to the double bond because of these end carbons, this one is the one that cannot form another tautomer. Okay, the other ones you can just have a look and you can see what they would do. Quite obviously in A looks incredibly similar here to the example that they've got, so that's just going to easily shift. That double bond comes down here and an H goes up from there, and that's fine. Okay, you can do similar things for the next one going the other way. So this one can come this way, this one can go that way. Okay, but the last one you can't. Okay, and that's it. Question 19. Which of the following compounds has non-superimposable mirror images? As soon as you see this, you know you are talking about optical isomers. And as soon as you say optical isomers, you're looking for a chiral carbon. That's all you're looking for. So in a chiral carbon, you've got your carbon in wherever it is, but central, I suppose. And we need to have 4 different groups. There has to be a different thing on each of these ends. Okay, so you go looking. So this carbon can't be because it's not got 4 possible groups, so it's got a double bond. This carbon's out because it's got 2 hydrogens. So A, no, not chiral. Okay. In B, this carbon has a CH3, an H, an NH2, and a C double bond O bond OH. So yeah, I'm totally happy with that one being chiral. To be clear on the rest, obviously this carbon's got 3 hydrogens, this one's got 2 hydrogens, this one has got 2 carbons on either side with the same kind of block, like CH2s, and this one's got 3 carbons as well, so no good at all. Sorry, when I say CH2s, sorry. That's a CH3 and a CH3. And for these carbons, again, 3 hydrogens, 2 hydrogens. This one again has got CH2, CH2 this time. This one's got 2 hydrogens, this one's got 3 hydrogens. So definitely B, no question. Apologies, there might be a blip about there because I, for some reason, had missed out question 20. So, compound X underwent elemental microanalysis and was found to contain 0.12 grams of carbon and 0.02 grams of hydrogen. Compound X could be. So this is basically an empirical formula question. There's lots of different ways you can set this out, but we'll go with one of them, I suppose. Right, so 0.12 grams of carbon. I need to get that out of the fact that it's carbon I'm looking at, and I want it to be a ratio I can work with. So I'm going to take 0.12 and divide it by 12 and get 0.01. Okay, because what I've also got is 0.02 grams of hydrogen, and I need to again use my relative atomic mass, this time of hydrogen, so that I've got something I can compare it to. Okay, so 0.01 and 0.02 is a really nice simple ratio. That means the empirical formula for this is CH2. Okay, and then you just do some work, and this is not, honestly, it's not that bad for this one. C4H4 on this one, that is not C to CH2. We've got C4H6 here. Nope, no good. C4H8. That's what you want. And just to check, C4H10 is also not CH2, so definitely C. Right, as I say, apologies, we're going to have to move back for 21 here. Okay, right. The mass spectrum of an organic compound has a molecular ion peak at MZ74. There were also peaks at 15, 31 and 43. The organic compound that produced this mass spec is... Right, okay, so they're not totally lovely in this one. You do manage to get rid of 2 of them with a one easy thing. Okay, it tells you that it's got a molecular ion peak at 74. So that means that the molecule has to weigh 74. Okay, so you can do some number crunching on this one. They're not all totally identical. So this one is 74. This one calculates at 74. These two calculate at 72 and 72. So we can get rid of C and D. We are looking at A and B. Okay, so A is this, and B is an ester. Okay, right, you are told 15, 31 and 43, and you now just need to sit and do a reasonable amount of calculator bashing to figure out if you can get the right numbers to work. Okay, 15 is not particularly helpful because 15 is obviously a CH3 fragment. Okay, 31 and 43, however, they are helpful. Okay, if I break this here, I can get a 43. Okay, if I break it here, I can get a 31. Something like that, and there's my 15 at the end. So this one works. Just to be clear, if I break this one here, I end up with a 45, which is why it's not working as well. There's my 15. Okay, so correct answer on this one is the ester, B. Okay, question 22. Structural formula of malic acid shown below. How many moles of sodium carbonate would be required to neutralise 6.7 grams of malic acid? Giving the formula mass of malic acid has been given for you at 134. Okay, right. Okay, so we are looking for neutralisation of this acid. Okay, so we have got an acid group here and we've got an acid group here. This is an alcohol and it's got nothing to do with it. Okay, so what I'm looking for is a normal carboxylic acid, and basically what would you do if you neutralise that to the salt? So what you'd be doing is producing the sodium salt, which would be that. Okay, so for every mole of this acid, of the malic acid, I need 2 sodiums. And if we look at what we've got here, we've got 2 of them in each sodium carbonate. So really what I'm talking about, for my acid to carbonate, I've actually only got a 1-to-1. Okay, so it's a little bit of extra work to kind of get where you're going with that, but yeah, you can just do that whichever way you want to. But I can see how you could go weirdly wrong in several different places, so just be really careful. Right, so I'm looking to, since it's a 1-to-1, I'm just going to work out the moles of malic acid. So literally just go in moles of mass divided by formula mass. You've been given everything in the actual setup of the question. So 0.05 and that needs 0.05, and there you go. Okay. Question 23, we're looking at a gravimetric analysis by heating 2.52 grams sample of hydrated calcium chloride. Tells you that you've got 2 formula units of water for every 1 of calcium chloride until it reached constant mass. What was the mass of the calcium chloride sample after heating to constant mass? And there's lots of different ways that you can do this. I think the absolute simplest way is just to run it as proportions. So CaCl2, 2H2O, and you're like, okay, how much pure calcium chloride would that be? So if I do the formula mass of CaCl2, and then obviously add 2 18s in for water, that gives me 147.1. Okay. My calcium chloride part of that was only 111.1. So if I started with a 2.52 gram version, okay, 2.52 divided by 147.1 times by 111.1 gives me 1.903 grams. Okay. 24. Which of the following techniques can be used to both purify and identify? Now that's important, so both purifying and identifying. Okay, so your first answer is correct. Distillation. Distillation allows you to separate out mixtures from liquids, and because you're pulling them off at specific boiling points, not melting points, that will allow you to identify as well. Recrystallization is a purification process. Solvent extraction is really purifying as well, and melting point is identification. So the only one which allows you to do both is distillation. And the last question in the paper is multiple choice. Okay, the progress of a reaction was followed by periodically sampling the reaction mixture and analysing it using TLC. The chromatogram for the analysis of one sample is shown. So you've got on this one a spot of pure reactant, R, a co-spot of pure reactant and the reaction mixture sample, and S is a spot of the reaction mixture sample. Okay, so which of the following conclusions must be correct for this thin layer chromatogram? Okay, so we've got here something that must be true. So here is our reaction mixture sample. Okay, and you look at it and you're like, okay, in the reaction mixture sample I have the same spot as I had with my co-spot of reactant, pure reactant and the reaction mixture. I have none of the reactant left. That's basically all I can say. I have used up all of my reactants. I don't know anything about impurities. I don't know anything about if I've got other reactant or other products that are present, because I can have 2 in the same spot. And I don't know if the reaction's complete. It might be a multiple stage thing and I've only got one of them gone so far, but I know the reactant is now all gone. I just don't know how much more I still need to do. Okay, so the only thing that must be correct, all of the other ones could be correct, is B, and that's the multiple choice.